Good afternoon, everyone. My name is Nicolas Petit. I'm the co-director of the cluster on technological change in society. It's great to see you. We are delighted to, I don't know, maybe close a year, I would say, with less activity probably, and especially a frontier talk. So as some of you know, I won't be too long, but as some of you know, and so this is well understood from everyone, in the cluster, we're trying to bring people working in hard science to talk to social scientists. That's one of the things we like to do and we try to do. It's a bit of a rocky experience sometimes because you have to, go over differences in semantics, concepts, linguistics, but it's always a very fruitful experience from past experiences. And so one thing we've done a lot in the past years, Marta, I'll say a word about our speaker in a minute, is we've invited mostly people working on communications technologies, digital, artificial intelligence, and so on. And when we started the program this year with Giacomo and Giovanni, we thought, yeah, it might be interesting to look into other areas of technology which are less talked about probably in the headlines of the main press outlets. And so that's how we did a bit of research, and we found your name and research, and that was very impressive when we read about it. So we decided to invite you. So the speaker today is Professor Marta Costa Figueiredo from the TU University of Technology in Eindhoven. So Marta is, so I'll go on a first name basis, is an assistant professor in electrochemistry, and she is focusing essentially on electrocatalysis and electrocatalytic synthesis for sustainable processes and production of high-value chemicals. So Marta is going to tell us more about what this means to a lay audience like ours. I want to maybe just stress for one second that Marta has been trained in various places. She studied in Portugal, did her PhD in Spain, then did several postdocs in various universities in Finland, Denmark, and the Netherlands. But interestingly, in the discussion we had before, Marta also explained that she was extremely influenced by her stints that she did in industry, and that left some, very good learning. And so Marta has a lot of experience across the board, and it's very helpful, it seems, to tackle issues in research which have very concrete applications in today's world. All right, so I won't be for any longer. The plan is we have about 1 hour, maybe less, maybe more, for a sort of lecture, and then we move on to more conversational modes with Q&A with the people here and in the Zoom room. Marta, it's a great delight to have you here, and you have the floor.
So thank you very much. It's actually my pleasure to be here today. First of all, the city is beautiful. Your installations are amazing. And I'm already enjoying giving a lecture sitting, because that's normally not the context that I'm used to. So it's the first time also that I'm talking for non-chemists. So please interrupt me if there's anything that sounds weird or strange, or you don't know what it means. And I'm going to start to tell you that the image that you see below is actually taken in our labs. That's what we do. We make this kind of very funky materials, I would say. This is copper that you probably know and have seen in your life. These are copper nanoparticles, and we use them to catalyze, to help us to proceed with chemical reactions. But probably this is how far I go in chemistry today. I do have some chemical equations in the middle just to give you a little bit of a flavor. But yes, but I promise you that I'm not going to show too much. Anyway, so first, to give you a little bit of a introduction. Well, Nicola already did quite a good introduction of my past, but so I have been doing electrochemistry for some years now. I started with my PhD in Spain, and along the way, along my postdocs, I specialize on electrocatalytic synthesis. So basically, we use electricity to do chemical reactions, and I aim at high-value compounds, and I'll go there in a little bit. But this makes sense because the Netherlands is also a country with a strong chemical industry. So we try to help them to become greener and greener. And here I also have some weird figures, I'd say, perhaps not for me, but maybe for you. But so one of the figures is a theoretical model of the image that I showed you before, right? A type of atomic arrangement that we all have in the material. And then the other figure, yes, I'm not sure. Oh, yes. Here, for example, this is a sketch of an electrochemical device. So a reactor, I'd say. And below there's just a sketch of some type of techniques that we use to optimize our models. But yes, okay. So I'm going to first start today by telling you a little bit what well, you probably know, tell you about energy transition and the role of electrochemistry on energy transition. Then I decided to spend some time in hydrogen, and mainly because I think hydrogen economy is more and more important. I don't do that in my own research, but I felt it was interesting to also put it as a point of view, because the most promising technologies for hydrogen are actually electrochemistry based, and at least in the Netherlands is a very hot topic. And I think in Europe, you probably hear a lot about hydrogen and hydrogen economy. Then the last 3 points are more related to my own research. So how do I apply electrochemistry and I see that I have synthesis twice, sorry for that, for electrocatalytic synthesis. Then also what type of things we do at the team that we have at Eindhoven working on this. And last, I want to give you a little bit of a flavor on a newly based institute in Eindhoven, where different disciplines are put together to bring energy systems up to front. So yes, global warming, I think that that's not new for anyone. Maybe today is a representation of global warming. It's very hot outside, and I heard that it's not very common for for here. But yeah, we all know, we all see in the news and everywhere that global warming is happening, and also we see the consequences and what causes that. So you've probably seen figures like this of greenhouse emissions, and that we are accumulating toxic gases in the atmosphere that lead to this greenhouse effect and to the global warming. And then there's consequences. The consequences are so serious and so important nowadays that you have 12-year-old kids demonstrating about climate change and that we should do something and we should take care of our planet. And if you think a little bit, probably in the head of most of the people, when you think about this pollution and these problems, people have these images in their head, right? And out of these 4 sketches, 3 are related with chemistry. Well, a nuclear plant, there's chemistry, well, a power plant, a factory. So everything has a little bit of chemistry. And I start being used that chemistry is normally associated with all the bad sides that we have nowadays in our world. But it's not always like that. But well, I'll go there later. I forgot that I still had this. But anyway, with this global warming, climate change, there's a global worry on stopping this from happening. And one of the examples is the Paris Agreement, where we promise to keep the global warming below 2 degrees, and if possible, below 1.5. This caused some chain reactions and also a European level and some policy making. And we have what we call the European Green Deal that says that in 2050, we should have no greenhouse gases emissions. So, and that, of course, there's other points on the deal. That is also that the economic growth should be decoupled from resource use. So it should not be based on what we can have. This is basically recycling and reusing, and no person or no place left behind. I like this sentence in particular because it's not very frequent to see chemistry and people related together. So, but basically, this means that by 2030, if we really want to commit with the European Green Deal, we should reduce our emissions by 55%. And all these efforts actually deal from the first European climate law that was approved in March 2020. I find this very interesting because it feels quite late to have a climate law at European level, especially when we have been talking about climate change for such a long time. But anyway, better later than never. So I think we should be already very happy. And actually, there's also good news. Not everything is bad. And if you look to this graph, also from a European Union study, by 2020, we were actually below the CO2 emissions that were targeted. So we were 11%, if I'm correct, yes. So 31% lower than in 1990, and actually 11% less than what was expected or planned to reach the 2050 goals. So I think it was 31%, the target was 20%. But actually, what I'm afraid of is that those were the easy parts to reduce. So when mainly, I think we all have contributed somehow. We drive more in shared transportation, for example, using public transports, not traveling so much in planes, all these small contributions that probably everyone makes help to reduce that. But now we need to change the big players. And in this case, chemical industry, aviation industry, all these ones. And I like this figure a lot because it's a little bit like recycling, right? So recycling is prolongating the life of a product, but we also need to do that with energy in such a way that we can avoid waste emissions and waste of energy. So ideally, we should have a circular use of energy. And again, in chemical industry, this is not even close to be done yet. And there's a lot of effort. And I think this graph also on the side shows that probably to reduce and to reach the 2050 targets, we need to increase 20% electrification. The electrification of chemical process, for example, that nowadays use fossil fuels as energy source. But also hydrogen is here as 10%, and that's the reason why I'm also going to talk about hydrogen a little bit today. Yes, but then it's like I mentioned electrochemistry quite a few times already. And I wasn't sure if you'll know what I was talking about or not. And I have a couple of molecules here, sketches, not even close to real ones. So don't blame me for that. But you have carbon dioxide. That is probably something that you heard about before and that you know, right? A very well-known molecule. If we want to break the molecule or to separate these atoms on a molecule, normally we use a temperature. That's how chemical industry works. You apply temperature and then you can break the molecule in the smaller parts, or you can even form new molecule bonds. For example, if you see this one here, right, there's some more atoms that didn't exist here. In this case, you also need to apply high temperatures, or sometimes you need to reduce the temperature, it depends, but temperature is the driving force for this type of reactions. And I have many other molecules over there that, if you don't know what they are, it doesn't matter, but it's just to tell you that you can really tune the reaction that you want to different products. The problem with this temperature is that it's one of the things that causes CO2 emissions. So to reach these temperatures, and sometimes you go to 400 degrees, you need a lot of energy. You need to burn a lot of coal to actually get all this. And this is not good. So what does electrochemistry can do? Well, we can, instead of using power and temperature, we can try to use electricity or electrons to drive the reactions. Slightly more complicated, but it works. So the best part of this is that you can actually use renewable electricity to drive the processes. So then you eliminate a source of carbon, and you eliminate all the burning of fossil fuels in this sense, because you use renewable energy and then you power your reactions and you get your products. So in this way, we can develop green and sustainable processes and help a little bit on the reducing CO2 emissions. And there's another very interesting aspect to electrochemistry is that you can use what we call the excess of renewable energy. So I have in the first graph, I have the increase of renewable energy towards the grid in the world level. And just to show it, in the last decade, it's increasing exponentially. So we are making a lot of efforts to actually transition to more renewable energies. But also what you might think is that wind, sun, they're not always there, right? You have fluctuations not only during the day, but also during the seasons. So, and sometimes when, for example, you have the most power coming out of the sun, it's not exactly when you need more energy in your house. It's because you also have sunlight, so you don't need lights, it's warmer, you don't need heating. So there's a slight imbalance in what you produce as energy and what you consume. So ideally, the chemical industry could use this excess of energy, and I went a little bit too fast, it's this excess of energy to produce chemicals during the periods of less usage. And in fact, I like these two Dutch newspaper examples. They are in Dutch, sorry. I don't know what, I cannot translate them myself either, but I know what they say. Is that in April this year, in 2 days, was the first time that the Netherlands produced more renewable energy than they could use. So there was an effective excess of renewable energy on the grids. So this all to show you that it actually makes sense, that is a reality, it's not so far from being possible. And yes, and this will be the ideal sketch in my point of view, in my research. Renewable electricity directly to a reactor that we normally call electrolyzer, and then to high value chemicals. And high value chemicals are fine chemicals. Fine chemicals is everything that you have in pharmaceuticals. Bulk chemicals that are all those that are made or that are needed to produce plastics in big scale, or cleaning products or everything. And then fuels. There's also a lot of research going into trying to produce synthetic fuels. And to give you a little bit of a perspective on the Dutch landscape, and I use the Dutch example because it's the one that I know the best, of course, because I'm working there. But in the Netherlands, there's a lot of commitment on making the chemical industry greener and on electrifying the chemical industry. And this, for example, is yes, a governmental lobby institution, well, not institution, but lobby system that's called Electrochemical Conversion and Chemical Materials, where you can clearly see this was taken from their roadmap, updated last year, that they are suggesting that we should focus science on electrochemistry processes to help on the transition for better production of chemicals. And of course, there's also hydrogen. So basically, these are the three main pillars that the Dutch government wants to look at: hydrogen production, efficient hydrogen production, green chemicals from sustainable sources, and green fuels. Yes, and as I promised, I start with hydrogen before I go to all the chemicals that I like. And yes, so believe me or not, in 1874, Jules Verne was already predicting that water will be the fuel of the future. I normally use this sentence to attract my students in the energy course because they like these facts. And I think it's very interesting that so long ago, someone already saw the power of hydrogen as a fuel, right? And why is that? Well, it's because it's a very abundant element. It's the lightest substance in air, is stable, and it has a very, very high density, energy density. So it makes all sense to use it as a source of energy, as a energy carrier. And most of the hydrogen nowadays is used for ammonia synthesis, and ammonia is one of the precursors for fertilizers. So that's why we produce a lot of fertilizers. Actually, the production of ammonia, this 55% is responsible also for 50% of the human food in the world. So you can imagine how big the industry for ammonia production is. Then we also use it in refineries, and refineries mainly are related with the production of fuels and diesels. 10% for methanol, precursor of plastics, and then 10% in other applications. So this is where we use hydrogen nowadays. So just its production from a renewable source will be important. But the future landscape on an energy transition scenario also foresees the use of hydrogen in transport, for powering energy, as feedstock, and also for heating, as a heating element, even in building environment. So we have been using hydrogen, but we also will need much more in an energy transition landscape. Yes, there's several advantages to this. This is just a summary of this, because if we produce it properly, it can be carbon neutral, so no carbon emissions for the production of hydrogen. Also has different storage forms, so for application wise, it's important to be flexible on the type of form, liquid, solid, or it can also be compatible with traveling into distance, or at least, and then there's very different ways to consume it, to make use of it in energetic terms. But the last sentence is very, very important. Hydrogen is only interesting if produced from renewable sources. If we're producing it from coal, then its benefits are known again. Yes, and just to also show you a little bit what are the bad parts of hydrogen is that, yeah, I like this sketch a lot, because it shows you for the same type of power, you have liquefied natural gas, ammonia, and hydrogen, 3 different types of fuels, or that can be used as fuels. And you can see how big are the tanks for relatively to each other. And that's the main drawback is from hydrogen. And it's easy to understand. It has a lot of energy per gram, but it's a gas also. So a gram of hydrogen is quite a lot of volume. But then if you compare the volumetric energy, right, the energy per volume, then it becomes very low. So you need to either find strategies to compress this hydrogen or to make it more dense, or otherwise its value is a little bit less. And there's actually strategies. Well, here I just compared the energy of hydrogen, the volumetric and the gravimetric density. Gravimetric is per mass and volumetric is per volume, compared with other fuels, with diesel, gasoline, and so on. But yes, so for hydrogen, there's different types of storage looked at. Compressed gas, that I think is a very easily understandable concept, right? You just compress it in cylinders. Then you can do that at the same time that you also reduce the temperature, so you can compress it even more. Liquid hydrogen, yes, it will require quite a big tank, but it's still possible. But then there's other world, I'll say, that is material based, that is integrating this hydrogen in materials. And I'm sorry for the chemicals over there, but it's just to show you that there's actually all lines of research where people look into how they can put hydrogen molecules into solids, for example, to be used to then be extracted and be used in local applications. And yes, this is a little bit related back with that hydrogen is only interesting if you produce it from green sources. And this led to 3 different qualifications. Actually, there's many more. You have a whole array of colors if you want, but I think the most common ones is gray hydrogen, blue hydrogen, and green hydrogen. Gray hydrogen is the hydrogen that we have been using in chemical industry, so mainly used with carbon emissions from fossil fuels. Then you have blue hydrogen that is produced the same way than gray hydrogen, but the CO2 produced, the carbon dioxide, sorry, produced is captured. That is a greenhouse gas. And then green hydrogen that will be produced with no carbon dioxide emissions. So this is also frequent in legislation policies, what type of hydrogen you need to use in a certain process. Yes. So that brings me to actually electrochemistry, right? because if you want to produce green hydrogen, the most common way to do it is by using electrolyzers. And in electrolyzers, what you do is that you get a water molecule, you apply electricity, and you break the molecule in oxygen and hydrogen. And I have this slide here, but this is very patriotic. Dutch people like it a lot because actually the first hydrogen electrolyzer was made in the Netherlands. So basically this person, Troost de Wijk, I hope I pronounce it properly, but there's, I think, no Dutch people in the audience, so I'm safe. He was trying to light a bulb, a lamp, right? And then he was applying some movement, it had some gold electrodes there, and then he saw bubbles coming out from the recipient with water. And then is when they suggested that water was being broken in two parts, two gases, oxygen and hydrogen. And if you ever visit the Netherlands and if you visit Leiden, there's a science museum where you can actually see the equipment that he used to do this experiment. But anyway, more molecules. I know that I promised there was not many molecules, but now I'm seeing quite a lot. So these electrolyzers are, devices where you apply electrical energy and you break water into two parts, hydrogen and oxygen. But of course, that hydrogen and oxygen, if you have them together, they are an explosive mixture. So it's not nice to have them together. So you need some kind of separation that is this orangey thing in the middle. Then this needs to be a permeable membrane, because you still need contact between the two parts of the cell. And this is the same thing that if you have a wire powering your device, if it's broken, there's no contact, right? You need to have it in contact. And that's why you need to have a porous structure in between the anode and cathode that are just the two solid electrodes in these devices. But you need to have electric and ionic contact all the time. So it's not a very complex reactor from the chemical point of view, but then you'll ask, so then why are not electrolyzers everywhere producing hydrogen? And the main problem is that they're not economic yet, and they are not efficient yet. And by economic, I mean, there's not enough production of this type of reactors yet to have economy of numbers, so that you reduce the price of the product because you're making a lot. They are not effective. Yes, also there's some parts that are dependent on rare metals, so that also makes it quite expensive. And then durability is also still an issue. So this all accounts for the price of these devices, and they are not very attractive yet. And then, of course, on the chemistry side, the efficiency is still quite low. So we still need to work on making better systems, better catalysts for this type of device. And yes, I like this scheme a lot because it shows a little bit everywhere that you need to work to make this system both effective, durable, and economically viable. So we need to do a lot of research on membranes. So these separators that I was telling you in the middle to separate oxygen and hydrogen, they're actually one of the problematic parts of the electrolyzers, because the membranes are not yet stable, and to be stable, they need to be very thick. And if they are very thick, they reduce all the efficiency of the process, because you start having bigger and bigger distances for the ions to travel. Also, the maintenance is still an issue. People don't really know how to do it yet. And we need to look into larger manufacturing, larger stacks. So, and yes, there's a lot of things still to be developed on these processes. Yes.
No, just a stupid thing. So the electricity goes on the cathode and the anode, and And you collect then the hydrogen, and the oxygen goes in the air. Is it collected as well?
It can be collected. A lab scale, we don't collect it. Oxygen can go to the air. It's not a problem. But ideally, you can collect it also because there's a market for oxygen. Another issue here is that the market sizes are not exactly the same. So you'll probably need more hydrogen than oxygen. So there's also studies on replacing this part of the cell with another chemical process that will also make a high value product.
Okay.
So imagine if you can have a pharmaceutical precursor being produced on one side and then hydrogen, then the person that needs the hydrogen or the industry that needs the hydrogen can also make money out of the other side.
Okay.
So this is, for example, one strategy to decrease the price or to make it more better, to make better economics. And they call it the double usage of one electron because,
Thanks.
yes, so you use the electron twice. Yes.
I also want to ask a clarification question. So what you're studying is how to use green electricity, the electricity that goes into this, right? This is that the electricity input must be green. That's what you're doing.
Yes, that's an assumption or that's a requirement. To be green hydrogen, the electricity that goes in needs to be green. Otherwise, it doesn't make sense anymore. And we tried, this is not my particular research, but there's also many groups studying how the fluctuation of the grid can influence this hydrogen production. If it comes, depending that all the system integration that is behind this electrolyzer. I particularly look into all these interfaces on the electrodes and the materials. Yeah. So yes, so that was a little bit of a flavor of hydrogen. I don't have many activities on hydrogen production, but now we're entering where actually my research is located. It's like using similar devices like I showed for hydrogen production, but for other chemicals. And yes, and I like to start by giving two very successful examples that I'm not sure if you know, but aluminum production is electrochemical based process. And it's one of my favorite examples because before an electrochemical process was used, it was more expensive than silver. And I normally also say this to my students in the lab because sometimes when you need to protect chemicals from light, they wrap in a lot of aluminum around, aluminum foil. And I normally like to say, be careful, that used to be expensive. But yes, and also all the cleaning, chlorine-based cleaning products that you have at home, they're all made by electrochemical processes. This shows that actually the implementation is possible and that it makes sense and it can be economically viable. We just need the proper market and development. And then what do we use as sources for the chemicals that we want to produce, right? We like to focus on widely abundant substrates, let's call it like that. And one hot topic in electrosynthesis is the conversion of carbon dioxide. Being carbon dioxide one of the greenhouse gases, it will be very nice to be able to capture it and transform it in something useful, right? I already gave a little bit of a hint when I showed what the electrochemical process is, that you can actually break CO2 into products. But what I want to show is that here, for example, you have a very similar device that what I showed before for hydrogen production. Basically, you have two electrodes, electricity coming in, and then you get out some products. Yes, CO2 conversion is still on its beginnings, I'd say. Let's say that we are in a scale of production of a few grams per hour of the products. Not really interesting to industry yet, but is a very, very topic of intensive research. I should have added a plot with the publications on CO2 conversion per year, and you'll really see how much effort is being placed. But then the biggest issue with this is that, as I also showed before, the number of products that you can have is huge. And if you imagine, you don't want that. You want something, you want a particular chemical to be produced. You don't want a mixture of chemicals. And why? Because you'll need to separate them. And this separation introduces costs and problems on the process that ideally you will not like to have. So people also look very much into this type of graphs to decide which product they should target or optimize their system for. And here, because there's two components, is the market price of the product that you want, but also if you need too much energy to put into your system to produce that product, then the normalized price decreased. So for example, ethylene, just believe me, it's one of the most desirable products from CO2, from carbon dioxide conversion, because it can be used as a fuel. And it's also important for chemical industry, for polymers and all these things. But when you see the amount of energy that this is by number of electrons, for example, the amount of energy that you need to put in is so high that the normalized price is really, really low. So sometimes it's more valuable to look into lower value, lower market price products, but at the end, they will become more attractive because the normalized price is lower. And for example, while I was working in a company of chemical technology, we were targeting this as a product, despite a lower market price. So again, there's still a lot to be done on this topic. And as, yes, this is, now I'm noticing this pretty much what I say to chemists, but the selectivity, that means that the selectivity of one product is not good enough yet. Most of the processes still have mixture of products, and that's very complex for chemical industry. Separation is actually very expensive also. So then to the cost of electrolyzer, you need to add all the costs of the separation process afterwards that also are big tanks, big separators, big reactors. So
Marta, can you, it's just maybe a linguistic question. So you mean the cost of separation, you mean the cost of breaking down CO2 into, okay, can you?
Yes, so the cost of separation, breaking down CO2 is associated with the cost on the electrolyzer, right, on the reactor. But then if you form, instead of one product, you form 3 products, they probably cannot be applied in the same process, right? Then you need to separate these 3 products from each other, even to sell them, right? I was trying to find a daily life example, analogy. Yes, it's like a distillation, right? From wine or from a liquor, right? If you want to have a high percentage of alcohol, you need to concentrate that, right? So you need a distillation process in between. Actually, that's a chemical process. And sometimes you need to do this also on chemicals, because if you have a chemical that is not 100% pure, then the price goes down. And imagine if you have 10% of a chemical in water, no company is going to buy it, because the price of removing that water to get the final product is very, very high. Yes.
But is the process the same? So it's just, can I have a cell that, depending on how much energy I input, provides a certain type of product? Can I have a multi-purpose cell that produces different outputs, giving the amount of energy I put? Or is the process completely different from producing the cool on the right that can be used for fuel from the very cheap one? I'm just trying to understand where you can use the same system for multiple.
That's a very interesting question, because the system can ideally be the same, but you can in fact select the product by the energy input. So it's actually a very clever association, because as I said, the amount of energy that you put for one and for the other is different. So that's one of the advantages of electrochemistry, is that by selecting the energy input, so the number of electrons that you put in, you can also be selective. This doesn't happen for CO2 though. That's it's one of the most complex processes. Also because the materials that actually break CO2 or form products on CO2 are very limited. So only copper does it so far. And then it's not selective. When it starts breaking, the molecule breaks and makes all these kind of bonds. So it stops being interesting.
Okay, and so do you know, so when you start the process, do you know what the output will be? You have an idea of the quantity, the variety?
You can have theoretical values, but they're normally very far from reality. So all these setups have, for example, energetic cost, right? Just from the reactor itself, you're going to lose certain energy, right? Because you need the electrons to travel and they pay a tool. So that's the first energetic cost. Then you can't really predict what the catalysis, what the interaction between your electrode, your solid, and your substrate is going to be. But we normally do the calculations afterwards. So you first have a hint on what type of products you have, and then you go to theoreticians and you ask them to have scripts that say, oh, you have this product because of this and this. It's difficult to predict.
We could extract some, so for sure you have done this a zillion times and try to find a neural network or something that could find the patterns and to provide a machine with an input that if I want to have reaction X, these are the probability, this is the amount of energy I need. I mean, of course, clearly, if this is not as predictable as such, you just cannot do it. But
it actually can, with the information already available, you can do it. And there's a lot of people doing it. There's so many people doing catalyst libraries. That's what they call. So basically, on the material that you use as an electrode, what type of products can you have? And machine learning for deciding what will be the reaction conditions. There's many other chemical parts to all this. This is a very simplified model of the electrolyzer. So you have pH, you have all the salts that are in there, the liquids, the solvents, everything. So there's a lot of research on machine learning, also on AI for electrochemistry, and for not only electrochemistry, but also catalysis, where you need temperature instead of electrons. Yes, so there is many people doing this type of prediction, but it's based on the knowledge that already exists. So they model some of the results that we have nowadays from the lab, and then from that they try to make assumptions and build up libraries. So it's there, it exists. Let's put it like that. Yes. And yes, and then the second thing that I have here is also very chemical, but mainly what I mean with these high current densities is that we need to have a certain reaction rate. So a certain production per hour or per minute or per second ideally, but we're not in the stage that we can measure that much per second. So, and that's actually a requirement for industrial applications. You really need to have these high current densities. That means that your reaction is very fast. Yes, and this is an example that I particularly like a lot. I have quite some research going on this, and this is for the production of fertilizers. So urea is a component of most of the fertilizers. And this, well, the industrial process to make it nowadays, it's a combination of two processes, actually. The first one, that the Haber-Bosch, that is the formation of ammonia. And actually this first process here, well, allowed the exponential growth of population in the world, because allowed the production of fertilizers. And then we have the second part that there is, where you have this ammonia entering another reactor with carbon dioxide to form this molecule urea. As you can imagine, I had it here, the temperature and the pressures of these reactors. So you can imagine how much energy you need to put in to reach this, right? And it's very easy. You just think about your electricity bill when you want to warm up your house in winter. So, and you just want to go to probably 25 degrees, imagine 400, right? It's really energy intensive. And what we would like to do in our lab is to replace this again by electrochemical process. So the same electrolyzer, just a different scheme from all the other ones that I showed before, with an input of renewable and electricity. And we use this molecule here, nitrate, as a substrate. And why do we like this one? Is because it's actually a toxic component in water. Yes, and it can be obtained from waste treatment plants. So basically I'll have the carbon dioxide from intensive industry, pollutant industry, or even from the air, from excess. I'll combine it with wastewater, and then I'll make a fertilizer. In one single step. So we will avoid to have this double step process, and in one single step, we would have urea. Of course, that if we will not get urea and we can only get this ammonia, I'll not be so unhappy. And the main reason is because ammonia is also nowadays looked as a possible fuel, so a replacement for hydrogen also. And the main advantage would be that ammonia is liquid. So you can avoid all the process of liquidification, compression, and the volumetric problem that you have with hydrogen. So there's a lot of research also looking to ammonia as a possible fuel of the future. But of course, I really like this urea one, and the main reason is because the interaction, the formation of a new bond between these two molecules is extremely interesting at fundamental level for me. And then the range of application is much higher. Yes, but then again, we have a lot of challenges to pass. And again, this might be a little bit scientific or chemical, I think, for chemists, but I'm going to try to explain. So to make the reaction to happen, you need to have you have an energy barrier, right? You need to overcome a barrier to have your reaction to happen. And we use catalysts, so materials, elements that help you on reducing this activation energy and to make the reaction easier to happen. And this is, for example, another material synthesized in our labs. I think this is like two metals together. So when we make these materials, we try to use them as catalysts to reduce this barrier. So this is what needs to still happen to make these processes an industrial reality, is that we need to get better materials on helping to overcome this energetic problem. And then we will achieve the high current densities or the high rates of reaction that I mentioned, and also the good selectivities. So we do much research on this topic. And then another thing that we should and we must and we need to pay attention is the materials. So unfortunately, many of the electrochemical processes, they like these noble metals, very rare, and they're also not green, because to mine these materials, you also produce a lot of CO2, and these materials are not available enough to all the transitions that we want to have in chemical industry. So we need to keep always an eye on this type of charts. That's actually from European Union, to see which materials.
I just wondered that these materials, these catalysts, are they used only once, so they can be reused in various?
If they are in a reactor, they can be used forever, is a long term, but they should not be consumed during the reaction. That's one of their characteristics, is that they are not consumed. Nevertheless, they degrade. So they are not one-time investment, but still you should not depend. For example, this here means platinum group metals. These are very rare metals, the most active for probably 90% of the reactions that I'm talking about, and they are really, really not available. We don't have enough for all the transformations. Actually, platinum is used, for example, in the exhaust of cars. And it's already a problem for this type of, to retain nitrogen oxide type of pollutants from engines. And they are already a problem here. And imagine if we now start using them to produce energy, it's unbearable. So we really need to stay on this lower part. Copper is still okay. For example, what is cheap? Copper is cheap. There's copper everywhere in our daily life. And it's still quite available. So it's a very good option for catalysis.
Aluminum requires a lot of electricity to be produced. So I see aluminum here.
Yes.
Yes, this is a very electricity intensive.
But it's still very available.
Okay,
I mean, available, and mining is not an issue yet.
right.
This is the last chart of European Union. It changed every year. So every year I try to have an updated version of this. But yes, but it's intensive. And then this is an engineering chart. Also very difficult for me. I'm not a chemical engineer, I'm a chemist. So this is for my colleagues at university, but it's just to show you that of course, that I've been talking about catalysis and molecules and everything, but that's not the only need that is now in the menu, is that we also need to do the whole process design, the whole integration system. So we need engineers that know how to integrate these new technologies in industry. And for example, how to stack cells. That means that how to put a lot of these reactors together so that we can really go to production rates that are meaningful and that can really make the difference. Or for example, we still need a lot of stability or durable and robust materials. And this is, for example, from our lab. We are trying to run a reaction, and this was copper deposited there. And after an hour, this black thing was the result. This definitely is not good. This doesn't help us yet. So we still need to do a lot of research also in these materials. And here with this example is the separator that I mentioned before for electrolyzers. There's still need for better membranes to be developed. So all these things need to combine together to actually make it a reality in industry. And yes, and I think that that's mainly the chemical message that I wanted to give you today, was that to show you that there's actually room for making electrochemistry part of chemical industry. There's advantages on using that. It can be a very good method to get green chemicals, but there's a lot of challenges to be met before we can go there. And I only mentioned the scientific challenges right now, but there's this, yes, public acceptance, integration, legislation. All these things still need to happen because they don't exist. And I think during lunchtime, I gave an example that Tata Steels is one of the biggest steel producers. Their factory is located in the Netherlands. They want to install a 1 gigawatt size electrolyzer for hydrogen production. And they predict 1.5 years of policy and bureaucracy until they can install it. And the main reason is because it doesn't exist yet. So it needs to be made by demand almost. So many challenges to be here. And now this is what we do in the lab. I just wanted to show a little bit how do I think that my research group can contribute to all this. So we look into processes that are industrially relevant, either because the product is of high demand or a bulk chemical, or because we want to really work in nearly industrial conditions. But we still do very fundamental research. That means that we look to molecules, atoms in a very small scale. And why we do it is because we try to understand from these very localized, very simplified models, how things could work in a more advanced situation. Of course, if we have something that is really good and is working very well, then we give it to our colleague engineers and they do the upscaling that I was talking about. I don't do that. I look into molecules in a very confined way to understand what they happen there. And so this is pretty much what we do. Also the techniques that we do a lot of in situ techniques. That means that we are operating the reaction at the same time that we are either looking at it by microscopy or following the product formation from many other techniques. And those are the examples that we have here. And yes, as sources of material, we look into atmospheric nitrogen, that is 80% of the air, it's nitrogen, so we can use that. All the nitrates that I showed you before from water treatment and also carbon dioxide. So we like to use either waste or very abundant molecules for our products. And yes, and this is the team. I think it's very important to show them because they most likely now in the lab trying to get some nice results for us. And all the 4 different projects that we have as main core of research. Not going to go into much detail. It's just to show you a little bit, the PhD students and what type of research they do, what type of materials they are using. And I noticed that maybe I just wrote the name of the elements, but it's not very easy. Sorry for that. Next time I'll change. But yes. And as I promised, I'll spend the last minutes showing a little bit all the efforts that Eindhoven University is putting on this energy transition. I decided I'll start with energy transition and end with energy transition with some flavor of chemistry. Bye. No problem, no problem. Thank you. Bye. Thanks. So yes. This also, I like this scheme because it's a little bit a summary of everything that needs to happen for energy transition. We need to change our chemicals and fuels, but we also need to think about heating systems, both for industry and for building environment. We have from production to usage, right? That's all the layers of these materials of this energy transition, integrating, for example, green feedstocks in our products. And everything that we like to do, not only for chemical industry, but also for transportation and for building environment. And that's actually the base for the distribution that we have at the Institute, or for the organization that we have in the Institute, because based on this, the Institute is divided in 4 focus areas. Of course, that more related with fuels, we have all the engineering part, we have the chemistry, that is where we are looking to new chemical technologies. We have a whole group working on sustainable how to get it in a sustainable way, of course. And then this will not make sense if you'll not have people looking to how to integrate all this in all the different areas of application. I'm going to be very brief on some of the members of the Institute and what they do. So we have in the focus area, these are the 2 PIs, Sylvia and Henk. And they look into new materials for heat storage. And iconic project as a heat battery in Eindhoven. It is like a medium TRL, or a technology readiness level system that is totally sustainable, and that they are trying with all these partners, all these companies, they are trying to improve and make it commercial. Then yes, I'm a PI also sorry for that. I'm a PI also on the Institute on the chemistry for sustainable systems, together with my colleague Adriana. And we have an electrolyzer, what we called, yes, the Dutch electrolyzer, again, very patriotic. But we have a lab scale electrolyzer that we are trying to produce on an industrial level with the collaboration of all these industries. So Eindhoven is very rich on manufacturing industry, so they all very interested on becoming pioneers on making these electrolyzers. Then we have system integration, where there's a lot of AI actually being developed, and to see how these networks could work, where can you have the best application, for example, for each of the technological solutions that we offer. And the focus area of engineering is very close to us, to the chemistry focus area. So we work very close together. The difference is that they also have another part that is metal fuels. So basically it's a project where you burn metals, so you oxidize metals, you burn, you get the energy from there, then you reduce them back, and you can continuously use iron-based, for example, materials to produce energy. Also, again, very, very supported by heavy industry, I would say. And yes, I had this slide to go a little bit more in depth on the chemistry for sustainable energy systems, but I do think that is a lot of chemistry. So maybe it's not so interesting, but as as a summary, we do develop materials and interfaces for energy applications. And this is not only electrochemistry, there's a lot of electrochemistry there, but there's also, for example, plasma catalysis, plasma chemistry, magnetic field induced catalysis, that is just basically all the ways to power reactions that are not dependent on fossil fuels. Yes, so at this moment, for example, in the chemistry focus area, we have 38 researchers, people doing a lot of good things in very different topics, from solar cells, for example, to polymers and also catalysis, not only what I'm doing. And I like to show off that we have quite an extended network of collaborations within these very good scientists. And in the picture, we have a lot of PIs, but also PhD students, postdocs, everyone that is contributing to make this a little bit more a reality. And yes, I want a little bit more into the Dutch electrolyzer. So at the Institute, we believe that you don't need to go big scale to develop a technology. And actually there's some publications on Science that says that a reactor on the size of a laundry machine or a fridge is the best way to learn, is the best way to accelerate the learning curve for developing a technology. So we are really focused on a small size device, in this case, the Dutch electrolyzer. We have close collaborations with the high-tech industry, as I mentioned before. And here we are really trying to learn step by step how this electrolyzer works so that we can apply it further, but not focusing on scaling up, just focusing on gathering as much information as we can from an operating system. And yes, well, of course, that we also look into new chemistries and that we are constantly looking for new solutions. That's a little bit the motto of this focus area within the Institute. And yes, and I think with this, I tried to give you some flavor of what I think is the importance of electrochemistry, how it is supported not only from TUE, but also from the Dutch government. This is the electrochemistry group. I showed them already, and all the funding agencies that are behind some of this work. And thank you very much for your attention. And I'm happy to discuss anything that you want.
Thank you, Marta. I think you deserve a little bit of applause at this stage already. It was excellent and full of learning for us, at least for me. And I'm sure it's the case for all the others. So we're now having 45 minutes for our exchange with everyone. Are there already some questions in the room? Zoom room, in-person room? Francisco, kick us off.
So I mean, the caveat is most of us are lawyers or political scientists. So if I say something completely absurd, please apologize. But all of these frontier talks for us, I think, like for me personally, are so enlightening that I always get this bunch of questions. I think the first question is, the process of breaking down CO2 seems absurdly easy in nature. It's happening every time and plants do it. And why is it so difficult for us to reproduce such a simple process as photosynthesis?
That's a very good question. And I and probably everyone working on CO2 conversion makes that question every day. And what enzymes do is very particular, right? But they also require very specific environments. And there's a lot of work being done on breaking down these enzymes, seeing the active site, seeing the metal that is in this active site, in trying to reproduce it in the lab, and it still doesn't work in the same way. I need to say to you though that CO2 is one of the most stable molecules that you can find. The energetics of breaking down that molecule are very high. And we still cannot mimic the catalyst that they use that plants use. Photosynthesis is like, I think I have been hearing about artificial photosynthesis since I started in electrochemistry. I don't think there's yet a process that is halfway efficient. Nevertheless, for example, for ethylene, there's publications out there with an efficiency of 70%, what is pretty decent. Challenges there are stability, for example, durability. These systems don't last for more than 5 hours. And you cannot have industrial process where you need to change your material every 6 hours. That would be just ridiculous. But yes, no, that there's a lot of research on trying to understand photosynthesis, and we still cannot reproduce it.
So basically we cannot reproduce the internal
The active
enzymes that,
center.
because they don't require a lot of energy. You know, I have a small plant with 2 leaves collecting solar power. Let's put, maybe this is very dumb again, but this is like for someone not on the field, this, I look at a plant, I look at 2 leaves collecting an absurdly small amount of energy from the sun, and yet they can break down CO2 every single day and produce oxygen. It's just insane that we just cannot replicate the process.
No, the enzymes, the replication of the enzymes exist, but you cannot use them on industrial scale. You cannot use them, you cannot put them producing 24 hours non-stop and being durable for at least 10 years. 10 years is more or less the industrial requirement for a system to work. Even accepting that you need to change some parts every 3 years. But you cannot do it with enzymes. That's why we try to look into the active center of the enzyme, what actually is, how the catalysis is working there, and trying to replicate it in materials that can last for longer and be highly efficient. And that is what this, that's the struggle. Because photosynthesis is well understood. So that's the point. We just cannot reproduce the same type of efficiency.
Okay, any other question? I have a few questions, Marta. Let me just ask you 2 questions, and you pick up really the one you prefer. So the first one is on, so the way I understand what you're trying to do is you're a scientist in a field in which the mainstream paradigm has been to apply heat to gas, and look at the reaction, understand this, and then reconfigure and adjust to generate other outputs. So heat is the inputs, and then you have outputs, and you work with this, and the field works this way for decades. And I understand what you're trying to do as, okay, we are going to change the method in the field. We are no longer, and we are going to change the method in a way which is more sustainable. We are going to use electricity, not heat, right? So you're basically changing the input of your science in the field. So from there, sort of 2 thoughts came up. One is, when you try to change the way a field operates, there's often some pushback in the profession, right? So when I talk to my friends economists, I say, you can work with your nice models of the economy, but it has very low predictability. You need to be open to new methods and stuff. And I often get a lot of pushback, like, you're a lawyer, you don't understand anything, which is fine. I accept that. But I wonder whether there's been like this sort of epistemological pushback from established norms and traditions in the profession. Second thing is, when you talked about hydrogen, then I thought to myself, oh, then the ambition comes full circle here, because you're not only changing the method, applying electricity, not heat, but also you're actually generating an output which plays, so you're not only using an input which is more sustainable, we're also generating an output which will contribute to increased sustainability. So if we use hydrogen for transportation, for instance. And so is this a killer application in your field? That's my second question, hydrogen.
Okay. Drawback from industry?
Yeah.
Yes.
Or scientists.
Totally. It's like, right now we are in a moment where industry just wants to explore options in case policies change. They will not change the methods just because they want to be greener. Unfortunately, that's exactly how it works. There's too much money involved, and building a chemical plant costs millions. They're not just going to disassemble the chemical plant because I have a very nice and sustainable process to make this chemical. Unfortunately, there's not, I mean, unfortunately, but I also understand there's a lot of money involved. So at this moment is exploratory field, and industry is very interested in whatever might come out, but they will not change processes unless they are obliged to. That's very clear. So yes, so there's interest, but they're not voluntarily changing processes. With hydrogen, it's totally different because it's a fair trade, yes, for industry. So they will change one part of the processes, but then hydrogen is used for much more. It's a chain chemical. So it feels more attractive to just replace one system to produce green hydrogen. And for example, ammonia can be synthesized with this green hydrogen. And then it's green ammonia, because then you basically don't need much more after that. So, and I think that's where the importance of hydrogen comes from, is because it's only one part of the process that can have a big impact. So industry is much more open to electrolyzers than anything else, and the chemistry that I like to study. That's good for patenting, and that's it. Basically, that's how it goes. But indeed, I agree with you that hydrogen is extremely interesting, because then also for transportation can be used. I think we discussed that. I don't believe that is the solution to all our problems, but is a very good solution for many problems. And that's why it's much more developed than everything else. There's a couple of megawatts, hundreds of megawatts electrolyzers already around the world. There's quite some companies, establishing companies in Europe now producing and selling electrolyzers. So that means that the technology is quite ready, and there's market for it because there's companies, and the companies, I think there's a company called Renewable that about 2 years ago was 10 employees, and nowadays is 150. 2 years to grow this much. I find it very impressive, very inspiring, perhaps. But yes, I think that hydrogen definitely is the flag of all this research, and is a very important one for energy transition for both applications, yes.
Okay, I have a follow-up question, or maybe not a follow-up question, but another question. So I was wondering whether in your research you are confronted with ethical problems, or whether your field thinks of the challenges in ethical terms as well. And if so, what are they?
I don't personally find yet any ethical issues, mainly because my research is very fundamental, so I still don't have any confrontation. And I'm not really aware of any big ethical issue, even with electrolyzers per se, for example, an hydrogen application. There's a lot of safety concerns, that's true. Landscape usage concerns also because of space, and especially in the Netherlands, it is a very small country, and we already live quite compact. Can you imagine when people want to use land for electrolyzers, then we start having a problem. But I'm not really aware of any big ethical concern on this energy. It's more, public acceptance is an issue. Chemicals are always related with very bad image in society. So you go to someone and you say, I want to put a hydrogen tank in your backyard. Probably not so easy. But yes. But those are mainly safety and acceptance.
Francisco, you wanted to ask Okay, there's a question in the chat. Yes, Giacomo, come in.
Hi, I'm Giacomo Cazzolari. I'm one of the coordinators of the tech cluster. So, Marta, thanks a lot for the talk, and really apologies because I was really able to jump in the very last minute, so I missed most of your talk. So I just have a very general question. I would be very happy to have your view on this. If you could somehow have access to the policy making that we are currently having on Europe nowadays, imagine yourself in a meeting with policymakers who are in charge of giving the direction of these new technologies. What would be your key suggestion there for them?
Very clear, carbon taxes. That's I think what policymakers need to make clear. We need to start increasing and having very strong carbon taxes, because we need to have incentives from big companies to change. And while there's no money involved, as I said, no one is going to change the production method if it's not required. So yeah, I think that if I will have access to policymakers, would be like, please increase and make very clear policies about carbon emissions, and that will help to develop the field and also make better processes.
So that would be the quick, let's say, quick and easy fix in a sense. But wouldn't that somehow displace interest in research like the one you are performing? So imagine that you have a very effective carbon tax system. Wouldn't that be a risk to the development of your own research, for example?
Yes, because then, and this sounds horrible to say, but I think that if there was a big carbon tax, then there will be interest from industry on changing and more money invested on research. Not only changing, but only in research. While nowadays, because at the end, industry is who has the real money to make a change. And this, for example, is a discussion that we have been having internally also on accepting or not contributions or funding research from Shell, right? And probably Shell is one of the most hated companies, probably around the world, very responsible for many of the problems, but also one of the stakeholders to change society and to change processes. So maybe I shouldn't say it publicly, but I think we should explore the money that they have and call it money laundering, research, or whatever, but I need that money to make my research possible. So I do think that when you change policies, you make big players like Shell or Total or to come to us and make real investments with really aiming to change the technology. While right now it's like a gray area, they want to look nice and they invest some money and they have some research, but they are the ones that can really change it. They have the money to do it. So probably we need policies and policymakers to force them to go in the right direction.
Thanks a lot. Thank you.
Giacomo, what's your question about was there an assumption in your question that with a carbon tax, a company that would make a killing while having, very unsustainable production processes, they would remain in business regardless of the carbon tax, and not incentivizing research towards less carbon intensive technologies like Marta's, or
Yeah,
so
in fact, that was part of my doubt. Exactly. I fully agree with I mean, I'm not so I'm an economist, so I don't have the I don't have expertise on the technical side, but certainly carbon tax are a quick fix that we need to use, probably more than what we are doing now. But you know, pushing very much on a policy tool like this will certainly displace interest from other technologies. So, and I have no idea where this could go.
Oh, there's one thing that is clear, that the policies cannot only change, for example, in Europe. I heard many companies saying, well, if we start having carbon taxes here, we go somewhere else. So, and that's dangerous field, because then we're not going to change the problem, we're just going to relocate it. So definitely we need global policies with greenhouse emissions, with carbon neutrality. Otherwise, we're just pretending to be a green Europe, but then the problem remains. So we're not going to stop anything. So yeah, what for me sounds extremely challenging. I maybe a little bit utopic to have a global policy around carbon taxes, and you know, sustainability and how green the process need to be. So I sometimes feel that this needs to come also a little bit from society, and green labels, people with preference for green labels, for recycled. I think there's a lot. Young generations are already doing that a lot, buying clothes that are recycled, not buying new, buying secondhand. You know, all this is changing a little bit. So imagine that you need to have a green label in every plastic component of your daily life. Some people rather have it, right? So, and then you start changing from the other side, not from the industry side, but from the society side. Maybe a combination of both, but.
Okay, I'm going to shift gears, but in a way it's related to the question that Giacomo asked. So Giacomo, you know, asked you a question and you said, okay, the remedy is a tax of some sort. I have a question about whether legal solutions like more or less intellectual property could help in this. What's your view on that? You talked about patents and industry wanting to patent technology. So what's the role of patent in driving or not driving the climate transition from your standpoint?
Money is ruling, and all the interest that I know in patenting is because they want to have the rights, right? So I worked for one of my postdocs was sponsored by a company, and we were doing carbon dioxide conversion for plastic precursors. And it was clear, the first thing they said to me was like, we're not going to change the process because of you, but we want to have as many patents as you can produce, because if we need to change, then we have the patent, then we have the rights. So I don't know if there's a direct consequence of patenting on energy transition, but I do know that there's a lot of research sponsored by companies that is all related about having that intellectual property of a certain topic. Dual feelings, yes, because it's good, research is done, it's bad, big names keep having the property, and it's all a money maker, right? And a little bit utopically also, but I really believe on a sustainable world, and then all the thoughts behind my science are contributing to something better. So it sometimes hurts me to think that if I'm partnering with companies because they are sponsoring the research, they're going to make money and a profit out of it. And it's not on the benefit of a better world, but just to get richer. So, but yes, but I don't really see a big impact that is not money-wise. Intellectual property.
Francisco.
Just a follow-up question on that, but do you feel that between researchers, so if a company is sponsoring, for example, a postdoc, is that postdoc, does the postdoc feel slightly pressured not to share the results, or is it sort of a mentality of very open data, open discoveries? Because that would change. Okay, that's sad,
No.
sad to know, but
There's confidentiality agreements, at least 99% of the time. You really have non-disclosure agreements with the companies, and everything that I published from those 3 years of postdoc was after a certain period of evaluation from the company, if they will use the data or not. And right now, some of the consortiums that I acknowledge the sponsoring, they have industrial partners, and everything that we publish, everything that we say needs to go through their approval. So that, no, there's no disclosure there.
that's maybe a big difference between both worlds. Is that because you don't see the sort of immediate industrial impact of a social science conclusion or discovery, we don't have, even if we are sponsored by private institutions, we don't have this sort of, there is an incentive, at least in theory, to really share the knowledge, and hive knowledge is a big thing. But yeah, I guess I understand if you're putting money into a postdoc and he finds the next Nobel on chemistry, you want to keep the Nobel for yourself.
Not only like that, but also, for example, discussions with companies. If I have a discussion with a certain research topic that maybe I want to have a partnership, all the documents, so if I have confidentiality issues because I'm a researcher, I don't want my ideas to be theirs. They don't read the proposals. It needs to be with no confidential words in the document, because they say that they can be contaminated with our ideas. But the other way around, I don't enter a lab of a company if it's not with a non-disclosure agreement. So there's NDAs all the time, everywhere. So there's no open science, unfortunately. Yes.
Okay, I have a couple of additional questions. So one thing, so we, over lunch, we discussed with Giovanni about something which was a bit intriguing. So we discussed this idea of converting CO2 from gas to solids. Yes. And you said you had, concerns, or very hypothetical concerns about it. Can you explain a little bit that's this idea of conversion of CO2 from gas to solid, and what are the concerns you have? So that was new. I mean, I never heard about that before.
Yes, so that's some technologies. We have carbon capture and utilization. That's mainly what I try to do also in my research, integrating carbon in new molecules. You have carbon capture and storage, and this mainly is what people are doing, putting barrels under the sea full of CO2 to store it there, stays there. And then the other alternative is halfway, that is to convert CO2 into minerals, mineralize it, and introduce it under the soil. So bury it, yes, in the soil. I have concerns because I think when we start having greenhouse gas emissions, we never thought that the consequences will be to the atmosphere by just concentrating those gases, right? We thought it was just normal. Yeah, we just produce our things, we have our industry, let's release everything. And now we are facing a problem from excess of concentration of these gases. So I have utopical concerns on putting it underground. We don't really know what consequences might have for all the equilibriums that we have on Earth, tectonic plates, and I don't know, that might be a little bit crazy and science fiction right now, but I'm always thinking, Earth always finds a way to reject what is not natural to it, right? And I'm afraid that we're going to face in 300, 400 years also a rejection of everything that we try to put under earth, right? And under the soil or under the sea.
So the more philosophical question is, as a scientist, where do you set the red line? So, you know, you think of, we say you have a concern here, but you don't know how serious the concern is. You don't have evidence about it. You can't really measure it. You don't know if and when it will happen. So what should be the red line for, you know, certain types of science? Where would you put them? Because, you know, in other areas, we hear like, you know, say again, nuclear, right? As we talked over lunch. People are like, you know, nuclear, you know, there's, you know, one nuclear plant that blows up every 30 years when it's placed on certain conditions. Let's just avoid that altogether. Precautionary principle. Right, you know, some people say it's fine, some people say it's not. But so, you know, how do you deal with, would you apply precautionary principle across the board? What limiting conditions would you place? How do you set the red lines?
That's a very good question. And I think that I set the lines on what nature does. Does nature do it? Yes, no? Then maybe we should reflect why nature doesn't do it. And why should we think about it twice? So yes, CO2 conversion, artificial photosynthesis. Okay, it shouldn't be harmless, right? We can't do it yet, but it's just a conversion with no direct implication to an ecosystem or natural boundary. I think when you start pushing natural boundaries, then that's dangerous, in my personal opinion, of course.
And so I'm gonna, you know, make you travel from to another area of science. If you think about transhumanism, for instance, so say, you know, I chop my arm and I replace it with a mechanical arm and I augment my brain with an artificial intelligence thing. That nature doesn't do that. Is this admissible?
I think it's admissible, and I'll fight you back, because I think nature does have regeneration. Humans don't have regeneration, yes. But some species do have, right? There's some type of lizards that they can grow members back. So it doesn't feel so unnatural. We don't have a natural way to do it, true, in humans. But I think...
What do you say about, so, you know, there's all these talking these days about recreating dinosaurs. So, you know, changing the genome of certain species to implant them with claws. And so is this something that, because that's nature. I mean, it's just nature in the lab.
My opinion, my opinion, don't mess up with genetics, with genes. That's the clear boundary that needs to happen through a long period of time, adaptation, mutation, change, right? It happens, but it's time to settle. Don't do it too fast, otherwise you might end up with very weird creatures. That for me will be a boundary, definitely. Genetic mutation is something that I think we should not even try. And again, might be just science fiction in my head, but
no, but that's good. I mean, it's always really hard. I think we in social science, the lawyers amongst us, we really struggle with defining, you know, how to socially control technological change. Mm-hmm. And where you set red lines, where you condition certain types of research or technology introduction. And so it's always helpful to, so your line, you know, don't mess too much with nature is a good line as a first principle. Giacomo has a question.
Yeah, and I'm sorry to bring you down to the earth with respect to these questions, Nicola's question. I have a really much more, you know, down to the earth question, and it's probably more a curiosity. When you develop your research agenda, when you develop an idea, how relevant is the cost effectiveness of the technology you are trying to develop. So is this something that you always keep in mind, or you just follow your curiosity and then at some point you ask yourself, well, is what I've done meaningful in terms of cost effectiveness? With cost effectiveness, I loosely think about the implications in terms of industrial production of the technologies they are after. Is there a continuous constraint in your research agenda, or is something that you check after some time?
I normally have it in mind, or I try to have it in mind, also because ideally we'd like to end up that this research ends up in industrial environment, in real application. So we need to think about cost effectiveness very early in the stage, otherwise we can never sell the idea to industry, even to a funding agency. If you don't show, or either it's very valuable and then it's worth to pay the cost, or then you need to make it accessible and cost effective to develop. So I think we do think about it in a very, very early stage of research.
Okay, so this is very interesting. Then how do you develop the skill for this assessment? I mean, think about I don't know, so technology that uses some rare material which is currently under not such a pressure in terms of demand. So current price could be very low, but if you develop the technology 10 years from now, the price of this material could skyrocket, and then the technology may become not so convenient, though, after all. So, I mean, it's quite difficult. I have a story on electric motor that were some technologies that were relying on rare earth, rare material, and before the development of the technology, the demand of that particular material was not so significant, and then the cost of analysis was quite convenient. But after some time, then we discovered that the material is concentrated in few countries with implications in terms of geopolitics, and then the demand of this material skyrocketed, its price as well, and then the technology, after some years, not so many years, became not so convenient. So it's a difficult task.
Yes, we have colleagues developing techno-economical analysis in early stage of research. We try to have that in mind, of course, we need to. But it's true that the cost of materials changes all the time, and especially we try to be very far from rare metals. Not possible all the time, but that's true. But yes, it's sometimes unpredictable. But we have groups at university just doing techno-economical analysis all the time for anything that we try to do from a very early stage. Not perfect, but is as close as we can be on having cost effectiveness always in our mind.
Very interesting. Thanks a lot.
These are really very specific, so a bit off topic so far. We're sort of more research agenda type. Now I have back to materials to two questions. The first is, do you think I saw the image of your electrolyzer, and it was fairly small, and then you had this analogy with a laundry machine. So is it possible that in the future, because one of the big things with hydrogen is, let's make hydrogen electrolyzers and put them in cars, and sort of put the batteries cars, and then my question was, could you minimize the electrolyzer to the point where you would have a car generating enough energy to activate the electrolyzer, have the input of the oxygen through a car or like a truck or whatever, and then to have a sort of self-sustaining cycle where the car is producing energy through movement. There is some sort of generator, dynamo, that produces energy that activates the electrolyzer. The input is there, just makes a separation, and the hydrogen part of the separation fuels the car. Is it so impossible to think of a situation where your electrolyzer is so small that can, you could basically have a car that runs forever just on air? So that's the first question. The second is the output of these cars. Like that's a big problem that I keep hearing every time I read. Like the atmosphere is not used to receiving so much vapor, like what the output of some of these batteries, right? That's one example of something that nature produces, but if it is produced in huge quantities, it can sort of imbalance. Is this a problem you are thinking about when I know you don't do hydrogen, but your colleagues that do hydrogen are thinking about?
So doing a very small electrolyzer, yes, we have some mini cars that we run for first year students on electrolyzer. So that's it will be difficult though to make electrolyzers so small that it's possible to use and reuse in a car. At least the idea that you're telling me about, I cannot really see it happening. Not so. You'll need to have electrolyzer to produce hydrogen, and then you'll need to have a fuel cell to that is fed on hydrogen to transform energy back. So you'll need to have 2 in 1 and very small, and let a lot of hydrogen, oxygen gases over there. I'm not sure how feasible that would be in terms of safety. Of course, that, as you said, efficiency is still very far. It will be impossible. So I don't remember exactly how much. I think this electrolyzer, the Dutch electrolyzer, is about I don't know, hundreds of watts or something like that, and it's 400 square centimeter. The electrode, the reactor is much bigger because you need everything around it. So I don't think you could have such a small electrolyzer to use in a car. But yes. Now concerning gas emissions, water should not be a problem. Water and water vapor should not cause any type of unbalance. And that will be the only outlet or output from electrolyzer.
What I've heard was that it could actually enhance global warming because it would also, like very high levels of vapor could just increase the greenhouse effects, not at the level of that other gases do, but if we would have every single car on the planet producing vapor instead of, it could actually augment. I don't know if this is true. It's like, again, I'm completely just reading things from the news, nothing else.
I don't think that, well, it's true. The humidity can enhance greenhouse effect. And that's why if you think in a greenhouse, it's a highly humid environment, right? But I don't think that will be the major problem if you will get rid of most of the greenhouse gases in the atmosphere. And that's ideally what you'll do if you stop producing CO2. So yeah, it's probably a good trade-off, but I need to read more about it also. So now you sparkle something. I need to look into it with more detail. Yes.
Okay, so we are very close to the hour. I want to close maybe with 2 questions, if there's no more question in the room. So, Marta, so yeah, I have 2 more general questions. So you are a real scientist, and we try to pretend we're real scientists too. Sometimes we manage, often I'd say, that's not always. And I've kept asking myself this question, what would be the, let's be arbitrary here. What would be the 3 cardinal rules of good science? What's good science for you or from your perspective? So that's the thing I'd like to ask you. And the second thing is, what do you read that inspires your science?
Okay. Interesting questions.
Yeah, I didn't send you the question. questions before.
No, but I like it. So good science, easy. Ethical science, target-oriented science. That means that you have an objective, you have a question to answer, and if the question is good, then you're going to do good science. That's my opinion, right? And third, honest science, and that's unfortunately something that I see less and less. I think that we see a lot of pop science, high impact science, very short papers with very little information, but very fancy titles. And my personal opinion is that, that's the wrong way to go. We should go back to really fundamental science and descriptive science and, things that, hypotheses that have been proven. Now, what do I read? I have a couple of scientists that I have as idols, people that I admire, that I like what they do. I follow their works and I tend to read most of their publications. And they don't necessarily need to be in chemistry or, well, normally in chemistry, biology also. I like biology a lot. So I try to also read there because I think there's always you can find very nice combinations in there. So that's the type of reading that I do to inspire myself in science. I like to also sometimes see some talks or videos of some of the scientists that I admire, just to get in the state of mind to get creative. So yeah.
Okay, that's very good. And you in your last remark, in a way, you uttered a reality which I think a lot of people here are trying to work on, which is to go a little beyond your own field of specialization and embrace interdisciplinarity. So it's great to hear this. The point on pop science is well taken. I was trying to find the name of your last paper. You said, avoid fancy titles. And the title was very technical, which I like, but, we are also in social science often incentivized to, so there's this saying these days that, you have to avoid a title that has more than 7 words, right? And so you need to go for the 2 or 3 words title because that's impressive. But sometimes I feel that the good old title with like 3 or 4 sentences made a better job at describing what we are doing. So it's not always easy to find the right equilibrium between catchiness and accuracy. But yeah, so it was a good, I enjoyed the points too, so that's great. Okay, so we are, oh wait, there's a comment in the chat. Morshed, sure.
I think I was spending some time thinking about whether I should ask this question or not, but maybe reflecting a bit on what others have already raised. I was curious about whether, I do research, which a lot of it is about blockchain technology. And of course, one of the big concerns about the use of blockchains is about energy consumption. And there's increasingly research being done on, how energy is being consumed, but also shifts towards using renewable energies for this. And I was curious whether you see, like, how you view this, about whether this is something in the conversation about the energy transition, whether these sorts of non-state applications of these sort of infrastructural technologies are something that is viewed with concern rather than something that can be shifted towards in a more positive direction, and whether hydrogen, for instance, could be one of the ways in which, let's say, the future mining equipment and so on is using hydrogen rather than using some other form of energy. Like looking at new energy sources, basically.
if I understand correctly, so what I personally defend is that you have different technologies for different solutions. You're not going to have one single energy solution. I think I even discussed this also at lunchtime. I think that mining equipment using hydrogen, not sure, but probably other type of synthetic fuels. Or I know, for example, there's a startup company from TU Eindhoven called Dense. They use one of the products from CO2 conversion, formic acid, to power small generators. And one of their biggest market right now is construction, because the power is not much, but it's enough for small, how do you call, lifts, for example, in construction sites, to replace some diesel generators that were used before. I think it's a very smart solution for their particular environment. That reactor is never going to power a car or something else, but for that particular local solution, it's very interesting. And that's what I believe in for energy transition, is that we need to stop being a little bit biased towards what is more popular, and again, going to pop science somehow, and think more on ecosystems, right? In a certain ecosystem, what is the best solution in terms of energy, what will be more practical, what will be less invasive, what will be more logical. So did that, but
yeah, I mean, like in the sense that, for instance, now a lot of it is about using solar energy. And so there's in El Salvador to many other places, we start seeing the places where mining is happening surrounded by solar panels. More like, even you were talking about how, you try to also make use of the like effluent, basically, like so there's also been like miners also put their machines next to places where like oil and gas drilling is happening, and using the excess energy from that also for powering some of their machines. And so I find that there's a lot of like, let's say, bootstrapped type of innovation happening as this concern becomes more and more prominent. And that's why, yeah, I was curious about what this could look like, and whether hydrogen was also part of this conversation. But thank you. No, it's understood.
But just to relate a little bit, I talked about everything that happens after we have renewable energy, and the other part of the scenario is that we need to get this renewable energy. So you need the PVs, the photovoltaics, you need the solar panels, you need the windmills, you need all these things that I didn't show in the picture, but they are also of concern. Again, I give the example of the Netherlands because it's probably the ecosystem that I know the best. The Netherlands has the North Sea. They are not concerned with having a lot of windmills out on the sea, offshore, and bringing renewables. But if I go to Portugal, people hate us to have a lot of wind farms, at least if they can see them. So this is the whole other part that I didn't talk about, and that you are also relating. So it's not only the hydrogen, then what is everything that is before that, and that I didn't put in the picture, but perhaps next time. So, yes.
Okay, perfect. So it's time to close. So I want to say again that our speaker today, Marta, has done a great job instructing us and allowing us to learn about our research, but more fundamental questions that surround the practice of science and chemistry and implications in the real world. So we are very grateful for your talk today. We will stay in touch. We'll try to stay in touch with you. If you ever feel like coming back to Italy, Tuscany, Florence, this place is your place. As our president often says, the European University Institute is the University of Europe. This house is the big house of every person that has an interest in social science here. So feel free to come with colleagues, alone, and we'll be very happy to discuss with you again. So big round of applause, and thanks for being with us, Marta.
Thank you very much.